Welcome everybody to our first topology Georgia number school, and I think many of you may be here at the same time, but this Georgia topology conference is a pretty traditional thing. It's been around, I think, and it's been run every year. So the big part of you are staying for the conference, and so we'll welcome you to that as well. Welcoming Mark Hughes from Brigham Young University. We're going to give the series number 1, right?
Thank you. Well, thank you to the organizers for the invitation to come and talk with you. I'll be giving sort of the first mini course, and so I'll give a talk today, and then one later today, and then kind of a couple others throughout the week. Really excited to do this. I was sort of told that we'd have sort of a mixture of levels of sort of experience and background in knotted surfaces, and so I sort of intentionally geared my talk towards sort of, if you've never really thought about knotted surfaces or haven't really seen much in knotted surfaces, my talk will kind of be an introduction to knotted surfaces. So if you've worked in knotted surfaces or you've thought a lot about surfaces and four manifolds, you've probably seen a lot of what I'm going to say, but hopefully I know there's kind of going to be a number of other really interesting mini courses with other sort of interesting topics in them. So my talk will sort of hopefully be kind of an introduction to a lot of what you'll see in some of those other ones. So as a brief outline, I'm going to give four talks during this mini course. The first one will be today. The first two will be today, this morning and this afternoon. I'm just going to sort of give an introduction to knotted surfaces. We'll talk about broken surface diagrams, and then also introduce sort of like some classes of knotted surfaces where you can sort of just create a bunch of examples. Later today, I'll talk about banded unlinked diagrams in S4, which is sort of a descriptive method for sort of talking about knotted surfaces. On Thursday, I'll talk about banded unlinked diagrams for surfaces in an arbitrary four manifold. And so, we'll still be talking about knotted surfaces, but instead of just everything living in the four sphere, we are going to ramp things up a little bit and talk about what does a surface look like in an arbitrary four manifold. And then the last day, I'm going to talk about braided surfaces, which is sort of the higher dimensional analog of, just how braids relate to classical knots. There's something called a braided surface, and we'll talk about how those relate to sort of knotted surfaces. Should I close this? Oh, and I'm going to kind of do a hybrid talk when it comes to drawing pictures. And I was asked to kind of give like a hands-on picture heavy sort of introduction to these things. When it comes to drawing pictures, with me, you either get fast or you get legible. I cannot draw good pictures fast, so I drew them all on the slides, and I'll kind of show them as we come along. So the first thing to talk about is what is a knotted surface, or a surface knot, or a two knot. Well, there's a few ways you can define it, but a knotted surface is a smooth embedding K of the two sphere into the four sphere. Okay, or no, sorry, I wanted to define it like this. So it's a smooth embedding of a surface into the four sphere, where F is a closed surface. Okay, so by closed, I mean compact without boundary. Okay, and S4 is the four sphere. Okay, so really, when we say knotted surface or surface knot, I'm really just talking about some embedding of a compact, closed, without bounded surface inside the four sphere. And oftentimes people like to restrict to the case where F2 is, like in general, F could be non-orientable, it could have positive genus, could be really any closed surface. Lots of times people really care about the case where, maybe you care about the case where F2 is the two sphere. And so when F2 is the two sphere, it's often called a two knot. Okay, so sometimes in the literature, you'll hear the word two knot. That is sort of just a special case of a knotted surface. Okay, where we're thinking about the topology of the surface as being a two sphere. Oh, by the way, if you have any questions, please ask. Whatever, feel free to stop me at any point, ask questions. So, everyone okay on this so far? Oh, and kind of so I'll switch between chalk and dry erase here. So stop me if you see me trying to use the wrong writing instrument on the wrong surface, okay? So sort of a way to simplify notation, oftentimes we're sort of gonna just identify K with its image. Okay, there's a tactile sort of fine motor skills difference between writing with the whiteboard marker and a chalk. So I'm learning that you have to apply different levels of pressure. Otherwise you break your chalk when you won't do that with the whiteboard marker. So oftentimes we're sort of just gonna think of the embedding as being the image of its embedding, and we don't really lose any information in that way. So I've specifically defined a knotted surface to be a smooth embedding, or to be the image of a smooth embedding, depending on how you want to look at it. That's not, by no means is that sort of a requirement. You can sort of loosen the smoothness and talk about, say, PL or PL locally flat, or just topologically locally flat. So there's different categories we can work in. I think Aru is going to be talking more about topologically locally flat things. So in sort of everything I say, we will be considering smooth embeddings. But one thing, one sort of consequence of the embedding being smooth is that we have this locally flat condition. Okay, so because K is smooth, every point, the image of K is locally flat. And what this means is every point in the image of this embedding has a neighborhood U, where sort of if I take the neighborhood U and I intersect it with the image of the embedding, that should sort of just that pair of spaces will be homeomorphic to the 4-ball with sort of the standard 2-ball or the standard disk embedded in it. So sort of this is just going to look like sort of the 4-ball, and I am restricted in the number of dimensions I can use, which is a common challenge we face when thinking about knotted surfaces. Okay. So in purple, we've got the 2-disk. In white, we've got the 4-ball. And every point in the image of our embedding should have sort of a neighborhood in the 4-sphere that looks like this. Okay. So we have this nice locally flat condition, which tells us that at least locally, there's nothing really weird going on. It really, all the interesting aspects of knotted surfaces is what comes from the global topology of the embedding. So any questions there? No? So I haven't given you an example yet of a knotted surface, and I won't yet. I will give you a non-example first. Let's cancel it. I canceled this already, right? Showed up again. It's going to pop up again. This will just be a challenge we deal with. That's okay. I think I didn't push cancel. I don't know if I pushed cancel last time. No, I did. Wait, if I turn off Wi-Fi, yeah, I think you're right. There we go. And turning off Wi-Fi is not gonna sort of ruin the Zoom call. Okay. So the first example we can think about is like taking a suspension of a classical knot. So think of sort of, suppose we have the trefoil living in the 3-sphere. We can sort of cone off the trefoil, maybe a sort of a schematic I'll draw like this. So we've got sort of the 3-sphere here. Okay, we can think of sort of the 4-ball as being the cone of the 3-sphere. So we can think of sort of a 4-ball living above the 3-sphere, but we can also cone off the 3-sphere below and think of sort of there being a 4-ball below the 3-sphere. Taken together, these two 4-balls give me the 4-sphere. And if I imagine having a trefoil or just some non-trivial knot living inside my 3-sphere, then I can, just as I'm coning off the 3-sphere, I can cone off the knot inside the 3-sphere. And what that's going to do is it's going to give me a surface. Okay, it's going to give me a surface which, I mean, the suspension of S1 is going to give me something that's topologically equivalent to S2, right? So when I do this coning construction or this suspension, I'm going to get a 2-sphere embedded inside the 4-sphere. So at least on the surface, this looks like it could be a candidate for a knotted surface or a 2-knot. However, if I look at sort of this cone point, any neighborhood of the cone point, and I guess I've drawn this here, so I might as well use the pictures I've prepared. If I look at a little 4-ball neighborhood of the cone point, the intersection of this suspension with the boundary of that 4-ball neighborhood is always going to be a trefoil. And since that's not topologically equivalent to just sort of the boundary of the standard pair of B4 or B2 inside of B4, that tells me that this little neighborhood is not sort of topologically standard. So it's not a locally flat surface, and therefore it's not a smooth 2-knot. Okay. So this is sort of our first non-example of something that at least could be a candidate for a 2-knot, but unfortunately it's not smooth because it's not locally flat. Any questions there?
Are the tips only points ruining the local flatness?
Sorry, are the cone point?
Yeah, like on points, only points actually ruining the local flatness.
Yeah, any other point in this thing will be locally flat. Yeah. So it's really just those 2 bad points there.
Is there any like a surgery to kind of resolve this problem later on, or it's we can rule out this?
I mean, you could sort of remove that 4-ball neighborhood and like if for example you're taking the cone or the suspension of like a slice knot, I suppose you could like remove the neighborhood and glue in like a slice disc, and that would sort of make it locally flat. So yeah, good question. So let's see, I can move the one. Okay, I can move this down. So, and is this chalk? This is chalk. This is not chalk, right?
The other way around.
This is not chalk, and this is chalk.
Neither show
No, I don't either.
There is a mathematician in the room.
The cloth is supposed to be for the white.
The cloth, okay, it had some chalk remnants on it, so that's where the confusion came in. Thank you. But please step in if I say any. I know there are some knotted surface experts here, so if I do say anything incorrect, feel free as the Rue just did to jump in. Thank you. So what we know what a smooth knotted surface is now. When do we consider 2 knotted surfaces to be equivalent? Well, for us, we're going to say 2 knotted surfaces say K1 and K2 are equivalent if and only if there exists an isotopy of the force sphere okay, which takes one of our knots let's say which takes K1 onto K2. Okay, so our notion of sort of equivalence for this talk will be just ambient isotopy. If we can isotope one of the knotted surfaces to the other by sort of deforming the ambient space, we're going to consider these two knots to be equivalent to each other. Okay, so there are sort of, so this is sort of the direct analog of what you would see sort of in the classical dimension. And so we'll sort of go that way. Now, what does it mean for a surface to be unknotted? Okay, so in the, yeah, go ahead.
Smooth isotopies?
Yes, so yeah, so I'll say smooth isotopy here, yeah. Okay. Yeah, when I say isotopy, usually I think sort of, but you definitely could consider topological isotopy for sure, yeah.
Also, B0 S is identity.
Yeah, so yeah, so if it's an isotopy, phi0 is just the identity map. Phi1, I want that to sort of take K1 to K2, and then everywhere in between, this is going to be a diffeomorphism of S4. And then I also want it to vary smoothly with P, I suppose, so yeah. Other questions? Yes, Karen.
For each of the times, does that have to like take the knotted surface to like a smooth knotted surface?
Yes, but it'll actually be, so by this condition here, because I've got this parametrized family of diffeomorphisms, if I look, if I think of my knotted surface, say K1 as being a map from F1 into S4, then when I sort of compose with the diffeomorphism, post-compose with the diffeomorphism, that's going to be another, because phi is smooth and it's a diffeomorphism, that's the composition will also be smooth, yeah. Any other questions? Okay. So what does it mean to be unknotted? I mean, in classical knot theory, we say that something is an unknot if it's sort of ambient isotopic to just the ordinary circle. Well, what's sort of the analog for knotted surfaces? That here. Yes, okay, that works. This looks like the whiteboard eraser in my office, and so it seemed, I was just a little suspicious that it was actually a chalkboard eraser, but it's proven itself to be quite effective. So, okay, so what does it mean to be unknotted? Well, there's actually a few sort of equivalent definitions of unknottedness, and maybe to see sort of why these are equivalent, or at least sort of to see why these are the correct sort of generalization, is in classical knot theory. What are some special properties about the unknot in classical knot theory that we might try to generalize to knotted surfaces? Like what is a defining characteristic of the unknot?
Bounds a disk in R3.
Yeah, so the unknot bounds a disk in R3, right? So it's the only knot that bounds this disk. Any other characterizing or sort of ways that you can characterize the unknot? Okay, so that would sort of bring us to an interesting question, the unknotting conjecture. I'm not going to generalize that one right now. That's a good question though, or that's a good way to characterize it. The other one that I'm looking for, this is kind of a fishing expedition, and one that I'm looking for, and why would you, lots of ways you can characterize the unknot. Why would you know exactly what I'm thinking when I'm looking for one? The unknot is also the only one that can sort of be projected to the plane with no crossings. So, if I take, say, the trefoil, and I try to I try to like push it down to a plane. Well, because the trefoil is a non-trivial knot, every time I have a crossing, I'm not going to be able to sort of entirely fit my trefoil into the plane. I'm going to have these little places where I have to sort of jump over to make a crossing. Okay, so the unknot is the only knot that can be sort of pushed down into the two sphere inside of S3. Okay, so we can sort of generalize this to knotted surfaces, and we can say that K is unknotted if and only if one of the following equivalent conditions holds. Okay, so the first is that well, let's look at this one here. So in the classical situation, we're living inside of R3. We have this sort of equatorial two sphere that lives inside of S3, and we want to push our knot down onto that two sphere entirely. Well, if we just jump up one dimension, we can say that K can be isotoped to lie in S3. Is everyone okay on the fact that we have some sort of copy of S3 that lives inside of S4? And so if K is unknotted, and that means that we can sort of push it into this copy of S3 entirely. Or the second condition, so this is sort of condition one generalizes this picture here. The second condition, we want to sort of generalize the idea of sort of bounding a disk. Now, because our, if we're dealing with a surface that's S2, what would the generalization of a disk be? Yeah, so if for example, if we're just looking at a sphere, then we would an S2, a copy of S2, then really we would just be asking, can it be filled in with a free ball? Okay. But remember, our knotted surfaces can have genus. So we could be dealing with something like this, something with positive genus. And in that case, to be unknotted means that you bound a three-dimensional handle body. And I'll say a word about what a three-dimensional handle body is. K bounds a three-dimensional handle body. Okay. So what do I mean by a handle body? Well, handle body, you just take a three-dimensional ball and then you glue onto it these little handles. And I'll talk more about handles and handle decompositions. I think tomorrow is when that'll come up again. So these are sort of like the simplest three-dimensional manifolds that we can ask, three-dimensional manifolds of boundary in some sense. And so we say that something is unknotted if it bounds something like that, okay, of the appropriate genus. So any questions or comments there? Yeah.
Correct way of defining a knottedness is non-orientable.
Oh yeah, so if K is non-orientable, I will, yeah, so I should have, in my notes I said if K is orientable. If K is non-orientable, then we have sort of a standard picture of what like a standard RP2 looks like, and there's actually two versions of it. There's sort of a positive RP2 and a negative RP2. And we say that it's unknotted for a non-orientable surface if it's a connect sum of a bunch of things like that. Okay, so there's a lot of interesting stuff and interesting examples that come up with non-orientable surfaces. When I talk a little bit more about like banded unlinked diagrams, I'll show you what this unknotted thing looks like. But this unknotted RP2 looks like. So, any other questions or comments? Thanks for bringing that up. Because I did want to clarify that this is for orientable surface knots or knotted surfaces.
Actually, for the second part, can we also ask that the 3D handle body only has like 0 and 1 handles? Or
Yes. So often when we're talking about like when we say a handle body, like I guess like when in like sort of a three-dimensional context, when someone says handle body, I think usually they mean something that's built up out of 0 and 1 handles. I guess when you're talking about like four manifold, you might say handle body, maybe you mean higher dimensional handle. I don't know if that's, but yeah, I guess sometimes, when I say handle body in this context, I mean something that's only built up out of 0 and 1 handles. Yeah. Other comments or questions? Yeah.
So if you're taking the trefoil and you take the boundary torus, that's an unmounted torus.
Yeah. So if you take the trefoil and you thicken it, then that torus is going to be unknotted. Now in 3 dimensions, it doesn't look unknotted, right? But if you allow yourself to sort of push it into the 4 ball, you can kind of unknot the trefoil and push it back into the 3 sphere, and now it's going to look like an unknotted torus. So sort of, yeah, this sort of bounding a handle body, the handle body could, if you pushed it into R3, the handle body could have knotted handles and everything. But you can kind of always undo knottedness like that. It's kind of like a 3-dimensional knottedness, and as long as we're willing to push into the 4 ball, we can kind of undo that knottedness. Yeah, it's a good comment there. Okay, so let's talk now about how to describe these things. I still haven't given you an example. I guess I've given you an example. The boundary of this is a knotted surface. Yeah.
I will give one comment. So in this case, you're ignoring the marking on the surface, and so you're just looking at the image.
Yeah. So you're saying like we're not looking at the actual embedding, we're looking at the image of the embedding. Yeah. And that kind of goes to that, like oftentimes we'll kind of just abuse notation and really just focus on the image. Yeah. Okay. So let's talk now a little bit about some examples, or at least build up some technology that we can use to create some examples. So the first type of I mean, really, we need some descriptive technology to be able to describe these things. Knot theory in the classical dimension has this beautiful benefit that you can draw pictures of everything you're working with. And so, you really can teach knot theory to like a high schooler on some level. For knotted surfaces, of course, we're dealing 1 dimension higher. So we have to figure out how do we even visualize these things? How do we represent them? And sort of the first way that we might try and represent these things is through what are called broken surface diagrams. And broken surface diagrams are probably the most sort of direct analog of how we typically do knot theory in the classical dimension, right? So in the classical dimension, we sort of, we have our trefoil. The trefoil is the only knot I know how to draw. You'll see this later. I could maybe draw a figure 8 on a good day. So what we do is we take our 3-dimensional knot, we project it down to a 2-dimensional space. And of course, when we do this projection, we want to sort of record when one strand is we want to sort of, when we're projecting down, we're losing sort of information in this projection direction. So we want to sort of record the fact that some of these strands sort of live at a higher height than the others. And so to do that, of course, we sort of break the strand at any point where, where we have 2 strands crossing over another, right? And the lower strand gets the broken strand, and that sort of records the fact that it sort of sits at a lower level with respect to this projections. We can do the exact same thing for knotted spheres. So for now, I'm going to kind of just work in R4 because notationally it'll be a little bit easier. But we can sort of record, or we can sort of think of having a projection. I'm going to call that projection pi. And it's going to take S4 minus a point, which is really just R4. And it's going to project it down to some R3. Okay. So just like projecting down from R3 to R2, we're just jumping up 1 dimension. And so to now, we may have to perturb our diagram a little bit, or we may have to perturb our embedding. So after perturbing K if necessary, okay, what we can show is that every point of the image of K under this projection is going to have a neighborhood that looks like one of these local models here, okay? So the perturbing is kind of just like, you know, in knot theory, if you picked a really bad projection, you could have sort of 3 strands crossing over each other, and you could have a multi-crossing, which people study. But generally we want to avoid that. So if we sort of wiggle our knot a little bit, or if we sort of adjust our projection direction a little bit, we just wiggle things a little bit, we're going to sort of push everything off, and we'll only get sort of double points here, okay? Now, the same thing is true sort of with knotted surfaces. If you pick a really bad direction, you might get something that's not sort of a generic immersed surface like this. But if you sort of wiggle everything a little bit, you're going to get sort of every point is going to have a neighborhood that looks like this, okay? Now, because we're dealing with surfaces now, we have sort of a little bit more complicated situation. And for example, for knotted surfaces, we get things that we don't see in the classical dimension. So for example, this third, so for example, we get points that sort of look locally just like an embedding. We get lines of double points where 2 sheets of the surface are going to intersect each other in the projection. We will also get triple points where 3 sheets sort of intersect each other in this way. And then we get these, I guess, these sort of branch points where there's something a little weird going on. This is sort of, if you've never seen this, you can think of that picture there as sort of being what you get if you took a figure 8 and coned it off, okay? So it's the cone over the figure 8, okay? So these things are going to happen with broken surfaces. There's really no way to avoid them. So we project everything down, we get some of these bad points, but just like in the classical case, we want to record enough information to then recover the sort of original embedding. And so the way we do that is we break the diagram as a way to sort of record the relative heights, just like we added little breaks into our classical knot diagram, okay? So, you know, if our point has a neighborhood on which the projection just looks like a local embedding, then we're fine. We don't have to do anything. If we have a sheet of double points or a line of double points, what we're going to do is we're going to break one of the sheets and make it so that there's a little gap in that sheet. And that little gap tells you that the blue surface with respect to the projection direction is a little bit lower than the red surface, okay? When you have a triple point, now you have to you have 3 sheets that are now intersecting in the projection. Now you have to sort of record what the order of the 3 sheets is. And so here, for example, the red sheet is the highest, the blue sheet is the next highest, and the green sheet, which we've had to break in 2 directions, is sort of the lowest of the 3, okay? Then the last one is this Whitney umbrella thing. And essentially in this picture here, it might be a little hard to see in that picture. Essentially what we have to do is, because we have this line of double points, we're going to cut one of the sheets, okay? And so essentially, what does this look like? I don't know if this picture is going to end up any better than the first, but we're sort of like cutting along one of the sheets. One of the sheets sort of passes through unharmed. The other sheet kind of, we snip it with a pair of scissors to sort of break it. And then we get this point where sort of the 2 sheets still meet. So if we do this to our picture, we get what's called a broken surface diagram of our knot, okay? And this is sort of the direct analog of a classical diagram of our knot. So let's pause there for questions. If you haven't seen this before, yeah, are there questions? Yeah.
Are you saying you can completely avoid transverse, like 1 point intersection of like or 2s?
Oh, like 2 sheets that intersect transversely in a single point? Yes, you
just completely avoid these kind of.
Yeah, because I mean we're projecting down to R3, and so there's no way that locally two-dimensional things can intersect. Oh yeah. Other questions? Yeah, all of this is happening in R3. Our original surface knot lives in S4 or R4, and what we're doing is we're projecting down to 3 dimensions. So this is something that you can draw And I say that loosely, I cannot draw these diagrams very well, but there's, you know, I'll have a picture that I did not draw that's a much nicer example. But yeah, so these things can be represented in 3 space, so. Any other questions or comments? Yeah,
So what's happening at the Whitney window?
what's happening there? What, I guess,
So I guess in the other ones, like maybe you have like 2 sections of the surface, like flat.
yeah, oh, yeah, so what's happening here is, like this is sort of locally looks like a little branch cover. And so what's happening here is when you compose the projection with the embedding, you're getting so I guess for all these local pictures here, if you were to look at like the differential, like the composition of the differential of the embedding with the differential of the projection, this would sort of be full rank. It would be the rank of that differential would be 2. At this point, sort of your differential is singular. And so you're getting like it doesn't look like a local embedding even if you restrict to a smaller sheet. I don't know if that answers your question. I don't think it did.
Is it, how about like you're just explaining all this broken surface singularity is it in terms of like a projection of some movies of the ours, maybe then that will explain that brand.
Oh,
umbrella thing is there.
Is that like embedded E to Z comma Z squared?
Yeah.
And then projected down to x1, y1, x2.
Yeah. So when we talk about, so if you've seen this sort of embedding so Gordana said this is like sending the complex Z into Z comma Z squared. So in 4 dimensions, sorry, like in 4 dimensions, this thing can kind of look like, let's see, what's the best? So we'll talk about, actually, we'll talk about movie moves. We'll talk about movie moves this afternoon, or motion pictures. And essentially, what this is going to look like is, let's draw like this.
Right, must move on.
Yeah. See, this is why I draw everything ahead of time, because so if you're sort of looking at a boundary of like this neighborhood, it's gonna look this little piece of surface is gonna look like this. And then what happens as you sort of move in towards this center point, what happens is this picture here is going to shrink down and get smaller and smaller, and eventually it's maybe not easy to see this. But eventually when this thing shrinks down, it's gonna shrink down just to a single point. This little unknotted thing that has a Lecture 1 in it. And it shrinks down to a single point. And it doesn't look like it would probably be an embedded surface, but this is actually a perfectly fine locally flat embedding of the disk into R4. And so with this little picture, all we're doing now is we're sort of just projecting down in this direction. Or sorry, we're projecting in the, what direction are we projecting in here? It's a little bit weird. Okay, I don't know which direction we're projecting in, but essentially, are we projecting in this way?
Yeah.
Daniel says this way. Okay, I believe Daniel. So we're sort of projecting in this way, and so somehow, like in the 4-dimensional picture, our strands sort of cross over each other. When we project, these strands have a singular point now. And so this is now a singular thing, 1 dimension lower. I don't think that was a very convincing answer, but I'll think about it and I can come back to you with a better description probably. Yeah.
Is there some sort of intuition as to why there's like 4 possible situations? Because when I go a dimension down, the way I think about it, there's like 2.
Yeah,
Like, what's the analog of dimension down, I guess?
the analog of dimension down. So this is this kind of comes from just studying like singular points of generic immersions. Maybe is the way to say it. And so like a dimension down, if you're an immersion, you sort of can only have transverse double points. Whereas once you go up a dimension, all of a sudden now you have a lot more, there's a lot more ways that something can fail to be a local embedding while still being an immersion. Yeah. Okay, good question. Any other questions, comments? Yeah.
When you're projecting into this direction, you don't have big tangents. Right?
Yeah, yeah, you sorry?
Yes,
Is there a difficulty with okay, so so just like in classical knot theory, we want to pick a projection direction. So I'm guessing there's like a Sard's theorem argument that you can come up with, which essentially says, let's see. Yeah, I think we could like come up with something in terms of Sard's theorem that basically says like the projection directions where you're gonna have the surface be tangent to the projection is going to be like a measure zero subset of the space of all projections, which you can think of as being R3 or S3, and so you can kind of, yeah. I could maybe make that a little bit more precise afterwards if you're interested. So, unless there's like a better argument, I don't know. That's.
I think the dimensions.
What's that? Oh yeah, because we're one dimension up, but the tangent space is also one dimension up. So I think the argument in S3 should just work, right? Is that what you're saying?
So I mean, you have one dimension direction on your surface, and you have a two-dimensional surface, so that adds up to 3. But you only have 3 dimensions.
Oh, so you're saying maybe it doesn't work?
I don't see direction.
Okay, I'll think about that. I'm yeah.
Don't you get the last picture whenever the projection changes?
Don't you get the oh, you're right. Yeah, well.
The surface is 2 dimensions and the tangent space is 2 dimensions. So you get 4 dimensions.
Yeah.
But so the tangent direction, so the projection direction will be tangent generically at isolated points where which we get to the last picture.
Okay. Yes.
Oh, sorry. I think yes. Yeah, sorry. Okay, sorry. The boundary is at the end.
I'll have to think. Let me think a little bit more about that. I'll come back with a better description of that, and I'll think a little bit about this like tangency issue and see what the argument would be. So, I do want to get to some examples. Oh, let me just say. So there's this just like Reidemeister moves. There is sort of a family of what are called Roseman moves that are much more complicated than Reidemeister moves, but they. But yeah, they give you sort of the same thing. If I give you a broken surface diagram of a knotted surface, if I give you 2 different broken surface diagrams of 2 isotopic knotted surfaces, those broken surface diagrams can be related by a sequence of what are called Roseman moves. They are the direct analog of Reidemeister moves. And obviously they're a lot uglier, but they sort of in principle work the same way. Okay. And I shouldn't say these are beautiful moves. They're a little bit harder to deal with than Reidemeister moves are, of course. So, so maybe I should just show you an example of a broken surface diagram. I am going to introduce sort of some of these families of examples a little bit later, but here would be sort of an example of a broken surface diagram of a knotted 2-sphere. So you can see that sort of like, we've got these tubes that are sort of crashing through these spheres. In some places, you can see that the sphere sort of has a cut in it, whereas in other places, you can see that the tubes have cuts in them. And sort of that just records the relative heights of the sheets of the surface, okay? So this is sort of your first example of a broken surface diagram. And honestly, we won't be doing a lot with broken surface diagrams, but I think they're sort of the most general, they're sort of the most direct analog of how we think about knots, and so I wanted to kind of show you some of these. But if sort of there's no other questions, I'll sort of start introducing a few families of knots that we can then sort of deal with think about a little bit in the problem session. So, any questions before we talk about different families of knots? Yeah.
It's really, maybe those two questions, but what's the difference between the second type of the intersection and the fourth type?
The second type and the fourth type?
Yeah.
So the double sheet and
The
the,
picture you draw on the whiteboard looks surprising locally looks surprisingly likely.
oh yeah, so locally, like down here, locally, it does look like the second type.
Okay, so
It's
probably-
really the fact that it's really the fact that you have that one singular point there. Okay, so I'm going to introduce a few examples of knotted surfaces. The first is what's called a ribbon knotted surface. And maybe in the interest of time, I'll just kind of show the pictures and explain in words. So the first kind of knotted surface is what's called a ribbon knotted surface. And the way you build a ribbon surface knot or ribbon two knot is by, first of all, you pick just a bunch of unknotted two spheres inside of the four sphere. So I picked some families here. I have 3 of them in blue. These are unknotted two spheres. Then what I'm going to do is I'm going to pick a family of arcs. Now, if you don't care about the genus, you can or you don't care about connectedness, you can pick any number of arcs that you want. If I want to create like a two knot or something that's topologically equivalent to a sphere, then I really just want to pick sort of, if I have 3 spheres, I want to pick 2 arcs, okay? And these arcs are going to start and end on the spheres, but otherwise they're going to be disjoint to the spheres, okay? So I've got 2 red arcs, and it's kind of hard to visualize maybe in higher dimensions, or sorry, in the 3 dimensions that we live in. But these arcs can kind of link the spheres. They can kind of pass in and out of the spheres in much the same way that an arc could sort of link an unknot or link a knot in classical dimensions, okay? So we have these arcs that sort of start and end on the spheres, but then their interiors are disjoint from the spheres. What we can do is we can thicken these arcs up, okay? So I'm creating a little thickening of these arcs. And then what I'm going to do is I'm going to serger the 2 spheres along these arcs. And by surgery, what I mean is I've got 2 copies. Here, I'll just sort of draw a simpler picture. I've got some arc here, okay? I'm going to thicken this arc up and make it a little tube. Now what I'm going to do is I'm going to cut a hole on each of these spheres, okay? And then what I'm going to do is I'm going to cut a hole on each of these spheres where the endpoints of this tube live, and then I'm going to glue in sort of the annular boundary, the other boundary component of the sphere. So I'm sort of cutting 2 holes in the spheres and then joining them with a tube, and the location of the tube is specified by where the arcs are. Yeah.
What's the dimension of the tube?
The dimension of the tube. So the tube is a So the arc is one dimensional. And I guess So these are not tubular neighborhoods in I guess
Yes.
Yeah, it's not a tubular neighborhood in R4. It's like a 3-dimensional thickening. Yeah.
Then you need some information, right?
Do you need extra information for framing? No. You really only need sort of the 3-dimensional thickening. So you can
I mean, if you want to get the non-orientable one, then you need to think about the framing. But if you want to get just the orientable one, then it is actually kind of like there's only a unique trait of framing.
Yeah, there's like a flip you can do if you wanted to get a non-orientable surface. But if you want everything to be orientable, then there's no sort of framing ambiguity there. So in this example, and I've only got like 2 minutes here, so we can this would be sort of the broken surface diagram you get from thickening up these arcs, doing a little 3-dimensional thickening, and then doing the surgery operation. Okay, so this is an example of a ribbon 2 knot, which is sort of the same. If you look at that broken surface diagram I showed you earlier, that is also a ribbon 2 knot. It's sort of built using this construction. Okay. Questions or something? Yeah.
How do you know when it goes up and when it goes down?
how do you know when it goes up and when it goes down? Like when
Through a sphere.
it goes through a sphere. So in this picture here, I've kind of like the way that I've drawn these intersections here, I've kind of drawn these in a way that kind of alludes to that. So in general, like the way that these things are broken just really depends on the height with respect to the projection dimension. And so like in sort of classical dimensions, you know, you'd have a band that sort of goes through like this. And so in this case, you'd have sort of you know, if you cap this off with a sphere, because yeah, let's see. So do you mean like how do I know which one is above and below from the diagram?
Doesn't matter.
Well, so in the diagram, because I've sort of projected the diagram down to 3 dimensions, I've sort of had to like to even just draw it in 3 dimensions. I've sort of made that choice already, if that makes sense. Whereas in 4 dimensions, like there still is a choice of sort of the way that it links. There's like 2 different directions, and the direction that's selected will sort of. It's just like in 3 dimensions, you can kind of link going this way, or you can link going the other way, and that will sort of determine which one is broken, which one isn't, based on the height of it. But it's a little misleading here because I've already drawn in 3 dimensions, so I've kind of made that choice already, if that makes sense. Yeah.
Why is there no the Z mod 2 framing issue?
Why is there no Z mod 2 framing issue?
If I just have a closed loop with odd framing, how do you resolve that?
A closed loop with odd framing?
And take the take the frame neighborhood.
I think we just choose like whenever we draw it, I think we somehow like already choose a frame. I mean
I think it's about parameterizations, right? Like your Z2 framing will give you a different parameterization. But we're not talking about the parameterization, we're talking about the surface. And so the 2 different Z2 framings will correspond to the same
underlying surface.
So it's kind of like the uniqueness of normal bundle thing rather than framing. Does that help?
I think Chewy is talking about pi1 of SO3. So you have to loop in and with them. You have to choose the normal direction to get rid of if you want a 3-dimensional.
Sorry, say that again.
So if you have an S1 and S4,
Uh-huh.
and the 2-way neighborhood is 4-dimensional, but you want a 3-dimensional thing. So you have to choose a normal direction to get rid of.
Yeah.
So you have a Z-mod 2 choice, which is pi1 of SO3.
Yeah, but
I think we somehow we like whenever we draw the surface like that, we are somehow like
We're choosing to put Oleg on the inside and the outside of the sphere when we draw this picture. I think determines point to this model.
yeah, so
yeah. So I think what I'm saying is like basically we are drawing just the chord, but actually kind of whenever we draw the chord, somehow like we know that the choice of the framing was already decided. Like, they're kind of having a such a.
I add a king that will change my surface.
Yeah, so yeah, like you can actually. So if you want to get a different framing, I think you actually change the diagonal.
so because
So
we're
like,
kind of
so like so like alpha 1, and you actually kind of you're thickening kind of like you have 2 choices, but actually whenever I draw that one, the chord diagram, I think I already somehow assume that this thickness is somehow fixed, and if I want to change the framing, then I actually change the like here like at the tip of this arc, I just make a little bit of like point like a kink or whatever.
Yeah.
So I just make such a thing and then change the framing.
Yeah, so these are so Sungwon alluded to like these chord diagrams of ribbon 2 knots. And so like the framing of the tubes is determined by just the blackboard framing. Is that what you're saying? Someone, yeah.
I think.
Yeah.
so, yeah.
Okay. So I'm actually over time by 4 minutes. I was going to talk about twist spun and roll spuns, but I'll start this afternoon with that. I think that means that in the problem session, there will be a couple problems that, if you haven't seen twist spuns or roll spuns, you won't probably know how to do them, but you can save those problems for later and just work on the other ones. So I'll kind of, next lecture, I'll start with the twist spuns and the roll spuns, and then we'll get into banded unlinked diagrams. So any other questions? Yeah.
I'm assuming that the reason this is called ribbon, there's some like
Yes.
intuition of what. Are we gonna talk about that in a future lecture?
Yeah. So why are these ribbon? Whereas like, yeah, so a lot of the properties of like ribbon discs also sort of carry over here. And in a couple, I think one of the homework exercise or the problem session exercises, it kind of walks you through like, you can always arrange a ribbon 2-knot so that it intersects the 3-sphere in a ribbon knot. It's going to be also the double of 2 ribbon discs. You can also think of like a ribbon 2-knot can be filled with a solid that sort of only has ribbon-like intersections, or it bounds something in the 5-ball, which sort of has no local maxima. So like basically everything you know about ribbon knots sort of works here as well, but just one dimension up essentially. So yeah. Okay, all right. I guess that does it for this lecture. We'll pick things up this afternoon. So, and I'll think about some of these parameterization questions or good questions. Oh.